Hi everyone, I am Dr. Surjit Singh. Today we'll talk about the Leetcode problem word search second. This is a good example to explain the use of try. Let us begin. We are given a board consisting of an array of letters. We are to search a given list of words in the board such that the letters in the word are adjacent, that is horizontally or vertically neighboring cells. We can move around the board and look for various words and check the presence of given words. One way is to convert the list of given words into set in Python. We know that the presence of a word in a set can be decided in a constant time. But since we are using backtracking, the effort will be reduced if we inspect just the prefix of the words using try. If the prefix is not present, there is no need to go further and we can skip the neighboring letters and backtrack right away. Try also helps in identifying words that share a prefix. Note, set is useful if most of the words generated during backtracking are present in the given list of words, while try is a better choice if the words generating during backtracking are rarely present in the list of given words. Consider this board, which is an array of letters. First, we will build a try using the given words. We define dollar as the marker named word key and initialize try as a blank dictionary. We process every word in words. First word is dig. Starting node for every word is the root try. First letter in dig is D. Key dig is not present in try, so we create a default entry in it with current letter D as the key, whose value is a blank dictionary, which becomes the new node. We show the node as a pair of braces in green color. Next letter is I. Within node, we make an entry for I. Its value becomes new node. Third iteration gives another nested dictionary. Processing of current word is over. In the present node, we save word against word key dollar. Next, we process oath that gives new entries in try. Try has now two keys D and O. Next word is dog. D is already present in try, so we don't create it but retrieve the existing D and its value becomes node. Next letter is O, for which we make another entry in node for letter O, and its value, that is empty dictionary, becomes the new node. Similarly, we create node for G in which we save dog against dollar. For the last word dogs, three nodes are already present. For S, we retrieve nodes D and then O and then finally G and make a default entry in it for S in which we save dogs against the word key. We have built a try using all the words. Number of rows and columns in the board are 4 each. Matched words is an empty list. Now we will develop the backtracking function to scan the board and turn by turn try every element on the board to be the starting word. Letter at 00 is H. We call backtracking if this letter is present in try, but D and O are the only nodes in try, so we move to the next iteration. Even A is not in try, that means no word starts with A, so we move on. O is present in try, therefore we will call the backtracking function in which try becomes the parent node. It is shown by magenta color braces. Letter becomes O and node is value of key O. It is shown by braces in green color. Dollar is not one of the keys there, so The pop function returns false. This indicates that O alone is not a word and we skip the if statement. We mark letter O on board as visited by replacing it with hash. This saves us from duplicacy in searching words. Turn by turn, we will process its four neighbors. Offset of first neighbor is -1 0, for which new row column pair is out of bounds, so we continue with next offset. Offset 0 1 gives position 0 3 where n is present. But n is not present in node, so we move to the next offset. Next offset gives position 1 2, which is within boundaries, but the letter x is not in node. Last offset gives position 0 1 where A is present, which is a key present in node. Therefore, we call backtracking for 0 1, in which node becomes a new value for parent. Letter becomes A and node becomes value of key A. Dollar is not a key in node, so the pop statement returns false and we skip the if statement. We mark A as visited. Normal practice of saving visited cells in a set has lot of overheads. So instead we modify the board now and will restore it at the end of the recursive call. We now process the neighbors of position 0 1. One neighbor is out of bounds and another is already visited. Out of T and H, T is the only key present in the node. So we call backtrack for position 1 1 and node becomes new parent. Letter becomes T and value of T becomes node. Dollar is not present as a key in current node, so word match becomes false and we skip the if statement. We now mark T as visited. H at position 2 1 is the only neighbor of T which is present in node. So we call backtracking for position 2 1 and node becomes new parent. Letter becomes H and node becomes value of H. This time dollar is a key present in current node, so we pop it out and value of dollar, that is oath, is saved as word match. The if statement is true this time and we append oath to matched words. We replace H in board as visited. No neighbors of 2 1 are present in node. Before closing the backtracking function, we restore letter H at position 2 1. As node is empty, we delete H from the parent node and get this new trie. This technique is called pruning of trie. Only leaf nodes can be pruned, so we delete letters of oath from trie as far as possible. This call of backtracking is over. So node and parent get their previous values restored from the call stack. We restore T at position 1 1. Node is empty, which means that there is no other word with prefix oat and we delete node T from the parent node. This call of backtracking is over. Now we restore A at position 0 1. Once again, node is empty and we remove A from parent node. This call is over. We restore O at position 0 2. Once again, node is empty and we remove key O from parent node. This way we have removed word oath from trie along with all its prefixes as they do not belong to any other word. This optimization will save time in future processing. Remember, duplicity is not allowed in the output list matched words. All calls of backtracking are over and we go back to the main function. Loop over row column will continue. None of the letters N, E, T, X are present in trie till we reach D at position 1 3, where another recursion starts, which goes to O and then to G. At this position, dollar key is found in the node which will be popped out and dog is saved in word match and then in matched words. However, this time node G is not a leaf node, so it cannot be pruned. We will continue to look for dogs as an extension of dog here before we conclude this call stack. However, dog present anywhere else on the board will not be saved because it has been pruned from try. Luckily, S is found as a neighbor of G. Dogs is popped out and appended to matched words. Now that node is empty, which means it is a leaf node now, so S is removed from parent and restored on board. G was not earlier a leaf node, but after pruning of S, it has become a leaf node, and we prune G and restore it on board, and then O. However, node D is shared by dig and is not a leaf node and will not be removed. We restore D without pruning. Program will continue further to look for dig till entire board is scanned. Next D is found at position 33. Recursive call for D is shown here. I is not a neighbor of D on board while we had pruned the O branch of D in try earlier. So this fruitless call of D ends quickly. It is clear that this pruning algorithm increases efficiency. When both the for loops of main function are over, it returns the matched words. Dig remains in try to show that no match for it has been found. There are M cells on board and L is the size of the largest word. All the M letters on board are tried as starting letters for word searching. For each one of them, cell in the initial recursive call has 4 neighbors. In each of the subsequent L-1 calls, maximum 3 neighbors each are processed, excluding the cell we came from. So time complexity is as shown in the expression. If total number of letters in all the words is n, then there are n nodes in try. So the size of try is of the order of n. Additionally, there are word key nodes in try that store all the words. Total space used by these nodes is also of the order of n. Maximum call stack size L is negligible. Thank you for your time. Please stay tuned for more such interesting problems.